Integral from 4 to 9 of quantity 2x plus 3 over the quantity x squared minus 6x plus 13. Okay, so it looks like there's a lot going on here. First thing I try and do is like, all right, we have a quadratic down here at the bottom, and I was like, all right, can I break this up into two polynomials? And not really, because the factors of 13 are 13 and 1, because 13 is prime. And so there's no way I can add or subtract those to make it 6. So that's not really possible. So I'm like, all right, maybe completing the square, maybe. This up here, it's like, well, we have, if we take the derivative of this, we get 2x minus 6, which is kind of like this up there. So you can almost do substitution, but not quite. And so I'm just going to kind of fumble my way through this and see if I can make something useful. I'm going to start by doing 2x minus 3. Now there's two things you can almost always do in math. You can add 0 or multiply by 1. So in this case, I'm going to add 0 minus 3 plus 3, which when their powers combine, you get 0. I guess their powers are 1 because 3 to the first, but it's not. That's not what I mean. You understand where I'm going with that. It's a Captain Planet reference. All right, so then I'm going to rewrite this part as 2x minus 6. And then I'm going to break it up into 2x minus 6 all over x squared minus 6x plus 13 plus, and now I'm left with 3 over x squared minus 6x plus 13. Don't forget the 1 there. Integral dx, integral dx. So now I've set this up in a way that I can kind of figure this one out. And so I'm going to say u equals x squared minus 6x, or plus 13. Therefore, du equals 2x minus 6 dx. And I'm just looking at this portion right here. And so I get integral. So this is the top part, so that's du, all over u, which will give us, when we take the integral natural log of u, which will be natural log of x squared minus 6x plus 13. And we're going to keep the absolute value signs there because this negative 6x could be negative. And so we want to make sure we're not taking the derivative of a, or we don't take the logarithm of a negative number. Universe exploding and such. Okay, so now we got that part done. So now we want to see how to do this one. I'm going to do what's called completing the square. So to do this, I'm going to call this 3 over integral 1 over x squared minus 6x. Now I want to make this a square. So what I do is I take this number, divide by 2, which is 3. It's actually negative 3. Square it gives me 9. So I want this number to be 9 over here. So what I'm going to do then is I'm going to do plus 13, because 13 is already there. But I'm going to subtract 4, and I'm going to add 4. Again, you can always add 0, which negative 4 plus 4, when combined, will be 0. But when 13 and negative 4 combined, we have 9. And so we can rewrite this as integral 3 over, let's see here, x minus 3 squared plus 4 dx. Now this one is a bit of a challenge. And so what we're going to do here is I think this is going to be a trig substitution. I know, I try to avoid trig substitutions whenever possible, not because they're hard, but because they're tedious. And I don't like things that are tedious. So we're going to start by saying we want a square here and a square there. So I'm going to say u equals x minus 3, du equals dx, because you take the derivative of that. And so we have 3 times the integral 1 over u squared plus 4 du. Okay, this is looking a little bit better because we've got a square here and a square there. So it's like this might actually work. So now I'm going to say that u equals 2, which is the square root of 4, tangent of w. And you'll see where this is going, hopefully. I'm also going to say that du equals 2 secant squared of w, dw. That's the derivative of tangent is secant squared. And then I'm going to say that w, I'm just going to rearrange this, equals arctangent of u over 2. And you're like, wow, why do we need that? It's like, I think we'll need it later. Whenever you do u substitution, it's usually easier to kind of get these out of the way. Okay, so now we got these. I don't want to use green. Gray? I'll do orange. Orange is underappreciated. All right, so now we substitute these in. And du, which is 2 secant squared w dw on top. U, oh, I need to find u squared as well. 4 tangent squared of w. There we go. So then we have u squared, which is 4 tangent squared of w plus 4. See, this is where the 4 is going to come in. And on a sidebar here, we know that sine squared theta plus cosine squared theta equals 1. Divide all of these by cosine. Actually, cosine squared of theta. But I just wrote cosine down there because it's convenient. And this is going to give us tangent squared theta plus 1 equals secant squared theta. So this is just the Pythagorean theorem. Yes, true, fact. And so from here then we can do some substitutions here. Even though I use theta here, it can be x or w, u, not a big deal. We're going to say 2 secant squared w dw over, and this is going to be 4 times tangent squared plus 1. So it'll be 4 secant squared of w, at which point the secant squares cancel, and we're left with, I'm going to pull this out over here, integral dw times 3 halves, which is 3 halves w, which we know that w, as we know from up here, we have 3 halves arctangent of u over 2. Now you can see why I kind of like to avoid trig substitutions when I can. Sometimes it's unavoidable, and sometimes, you just have to be comfortable with discomfort. Sometimes things in life are unpleasant, such as trigonometric substitutions. X minus 3 over 2. Yes, so that's our, that's the second portion here. Did I leave the 3? So I need to remember the 3 over here. And so when we combine all this equals, I'm just going to copy and paste. I know it's poor form, but it is convenient. So we have natural log of x squared plus 6x plus 13. And then we also have, we're going to add to that 3 halves, but I kind of dropped the 3 there. No, did I leave the 3? Nope, I kept the 3, so I don't have to put on an extra 3. Just the bookkeeping of that kind of stuff is kind of challenging sometimes. And then we're going to add on a c, unless it actually wanted us to, nope, it wants to solve from 4 to 9. So from 4 to 9. I'm not actually going to solve it because that'd just be tedious. But what we'd do is we'd plug this in, we'd plug 9 in for all of this. Then we would do the same thing, plug 4 in, and we subtract the first part from the second part, and we just evaluate it. So we could do that. I don't want to do that right now because it's long and tedious, and that's algebra, which though I can do, I'm almost guaranteed to make a mistake and look foolish. And I try to avoid looking foolish, especially for things that don't have a lot of value added. So that's how I would approach this problem. This one's pretty challenging. Didn't really know where to go when I started. so I just kind of fumbled around. First thing I did was I broke this top part up into something that I could do u substitution on, which gave me this first integral. I was then left with a second integral that did not have an x up top, but had an x squared on the bottom. That's like, well, okay, maybe a trig substitution would work. So I did a completing the square. It kind of sort of seemingly magically worked out well, and I was able to do an arc tangent integration there, inverse trigonometric integral. So a bit challenging, kind of cumbersome, but this is a very possible problem to complete. So hope that helped. I will see you on the next problem.